to being the chairman of this session. So um, oh, it all works out fine. I noticed that he was pushing me outside, but that didn't realize that I was actually the one supposed to be chairing the session. Anyway, the floor is yours.
Thank you. Thank you very much. I'm Ivair Santos from Maringá State University in south of Brazil, 3,000 kilometers from here, but very close to Iguaçu Falls, only 400 kilometers. A little bit far. I would like to thank Dr. Igor, Dr. Eiras, for the kind invitation to show you what we have developed in Maringá in the last years, considering the study of multiferroic materials. And my talk today is about domain structure, domain walls, and correlated properties in BiFeO3-PbTiO3 multiferroic compounds. And this work is, as you saw, because André showed us an ancient picture when I was a student of Dr. Eiras. Dr. Eiras was my doctorate advisor. And this guy, Valdirley, was my former doctorate student in Maringá. And this work is basically his PhD thesis. Today, Dr. Freitas is our colleague in State University of Midwest in Paraná State. This is an outline of my presentation. I'll show you this compound that's very interesting for practical applications, and discuss some microscopic properties that we characterize for this material, and our microscopic view of these properties, and try to correlate these properties with domain and domain wall in these materials, and my final remarks about the subject. Okay, BiFeO bismuth is a very well-known prototype phase for multiferroic material. It have a weak, but still is there, coupling between the order parameters, electric and the magnetic order parameters, magneto-electric coupling. And if you use other prototype material for ferroelectrics like lead titanate, you can dilute this lead titanate in BiFeO with a similar magnetic structure. The case here is that you broke the cycloid period that prevent the microscopic magnetization in BiFeO by using diluting lead titanate in BiFeO. And this replacement breaks this cycloid. This is very interesting because you release the magnetization of the system. But also you can have very interesting electric and piezoelectric properties for this system. In fact, these materials, these solid solutions, they are multiferroic magnetoelectric materials with magnetoelectric coupling at room temperature. Strong candidates for practical applications in smart device because some of these responses are very high in these materials in bulk form. But the understanding about the properties is somehow difficult, as I will show you. Usually, you have these two kinds of space groups for these materials, tetragonal and the rhombohedral phase that are shown here, the polarization directions in these two kinds of phase. And the magnetic ground state is an antiferromagnetic material. Considering the properties of this material, you have this material is ferroelectric, piezoelectric, and a weak ferromagnetic or antiferromagnetic material. And I put here in this, I marked these two piezoelectric responses, the G33 and G15, the shear and in-plane response for piezoelectric is a very good number, very close to the PZT5A, that is the most used piezoelectric material in ceramic form, obviously. Okay, we did a lot of characterizations to see how is the microscopic response of these materials. When you have some characterizations to see response that are from the old materials, you have some problems, or not problems, but effects that is very difficult to separate or to split from your main results. For example, properties tested by probes or techniques that came from artifacts that mimics ferroelectricity, like capacitance, response, polarization. We have usually size effects, relative fraction of surface interface atoms, and the other problems that are related with the size of the polycrystal. And also scaling effects that are there regardless the physical dimensions, like external strains, impurities, finite dimensions, and so on. And this extrinsic response, we have some then that originates from the domain wall, like electromechanical, permittivity, hysteresis loops, that is very linked to the domain wall movement, and the extrinsic response that arises from the lattices, spontaneous polarization, permittivity, piezoelectric response. Okay, to see these properties, we did some, we create in solid solutions of a BFPT, we replace lanthanum to control the tetragonality factor of the samples. When you have a phase transition from a purely tetragonal sample from one purely rhombohedral sample, if you have 30% of lanthanum in a site of this material. This material without lanthanum has a tetragonality factor of 1.18, 18% of the tetragonality factor. If you put lanthanum in the system, this tetragonality factor is decreasing, decreasing, decreasing. You have a phase transition for only a rhombohedral phase, and here you have like similar morphotropic phase boundary. This material, as I told you, is they have a magnetic response that increases with lanthanum addition, and also a ferroelectric response that have that is better for 3% and 5% of lanthanum in this structure. When this concentration grows up, the leakage current prevents the correct characterization of the ferroelectric response. What lanthanum addition do in this case? Increase electrical conduction, losses in hysteresis loops also increase. You see here that concatenation is not good. But on the other side, the magnetic properties also increase. We did some magnetoelectric characterizations, and the magnetoelectric coefficient is one of the highest for single-phase materials that you see. There's a sample with 5% of lanthanum. But here we have a question: how lanthanum doping in a site substitution works? What can be turned in this case? Potential step at the ferroelectric domain walls, magnetic response, ferroelectric response, structural arrangement. This we are seeing our results. To see this better, we did also high resolution synchrotron X-ray diffraction and also high resolution neutron diffraction to construct the magnetic lattice of this sample, to propose the magnetic model for the magnetic ordering, and also to see how is the complete structural arrangement of these materials. And this model, important result that we have, that the magnetization and the polarization vectors are not in the same, they are not in a regular angle here between them is not 90 or 180 degrees. It's different, for example, from BiFeO. And our schematic structural model is here for the hexagonal cell and the pseudocubic cell for magnetic moment. And P and M vectors are not perpendicular or parallel. This is the key result that we published in Journal of Applied Physics. We did also simulations by using maximum entropy method, using the results of X-ray diffraction, high resolution X-ray diffraction, to see how the charges are distributed in surrounding each site in this material. It's a very interesting technique because you can, using this technique, you can see or try to see how is the behavior of polarization in your sample. You did the simulations for some special directions, 001, 110, and we see that for different concentrations of lanthanum, we have some change in the electron concentration closer to the sites. They have some hybridization in some directions. For 200, 200 is displayed here, no, and 100 is this phase. 200, 100. You have change in electron concentration for some bonds in these materials, and you have for tetragonal and for rhombohedral 110 direction of polarization. As we have all positions refined by Rietveld refinement using X-ray and Newton diffraction, you can do the simulations and see how the structure is tilted to accommodate these positions in the samples. And this, please forgive me because this is not a good image, but with lanthanum concentration, have a magnetization increase, the exchange, the distance for super exchange in the magnetic interaction decrease in this case, and the angle increase, the super exchange angle increase with lanthanum increasing. When we did this, we still have a lot of questions to be solved. How lanthanum doping or generally A-site substitution works, in fact, in this kind of material. How to correlate size and scale effects here. And the most important, what can be turned in this case? The electrical potential, step at the domain wall, because it's an interesting problem for new generations of electronic materials, the electrical conductivity of the domain walls, the magnetic response, the electrical response, and the structure, where these materials can be effectively applied. And they did to do this, we try to see microscopically what is happening with our sample. Try to connect macro properties to micro characteristics of our sample, determining the domain structure, looking for the domain interface. String response that originates from domain wall or phase boundary motion, and intrinsic response that arises from the crystalline lattices or the thermodynamic stability of the system. We did some transmission electron microscopy characterizations in this sample that have 3% of lanthanum. Why this sample? Because this sample we have tetragonal and the rhombohedral phase coexisting in the same material. And we did this preliminary analysis, and this is we can recognize some stripes in two different grains, some stripes that in the electron diffraction, like not satellites, but is not so so well arranged, this electron diffraction result. But these stripes are here in this result. By using high-angle annular dark field analysis in scanning transmission electron microscopy, we did this analysis, and this analysis is you can measure, have a contrast for the atomic number of the atoms that you have there. And you see this region, we have a high atomic density in this interface. A high atomic density, and the question is, this high atomic density can be a spurial phase, can be a defect. What can be this high atomic density in this sum of this very thin interface? We did EDS mapping for these regions, and you see for each of atoms that we have in our chemical formula, we have no concentrations of atoms in these stripes. It's an indication that our sample is very uniform. Chemically speaking, it's very uniform sample that have no clusters of different or one concentration from one kind of atom in this stripe. For example, it's not only lanthanum or only lead or so on. It's a good result because we see that our sample is chemically homogeneous. We use high-resolution transmission electron microscopy to see this interface that now is here, is indicated here, this interface, and to measure this interface, the distance between this interface. And this distance between this interface is almost 23 nanometers, and the crystallite size, by using Scherrer equation, we found 26 nanometers. In this case, the agreement is very good for this. And this is a crystallite that was measured by X-ray diffraction. It's very close that this domain size, now we can call domain size, measured by high-resolution transmission electron microscopy. We did also some simulation, because when you have the information for high-resolution transmission electron microscopy, to discover what is the structure, you need to do some simulations using a Java electron microscopy software, and we simulate the structure with P4MM, this space group, and there's a perfect matching between the simulation and the real image. It's an indication that our structure is in fact that was observed by X-ray and the neutron diffraction. And when you do the simulation, we can also see how what atom is in each column once the electrons that are transmitted. We see the columns of atoms that electrons goes inside. And it is the atoms for this simulation. We take two regions to do electron diffraction and also simulate with this space group, electron diffraction simulation. They have a very good agreement with this structure. That is this region 2. You have this A and C lattice parameters for P4MM space group. When you do this electron diffraction in this area, in the frame 1, we have the same of this, but now tilted by 81.8 degrees. It's almost a 90-degree tilt between this side and this side of this interface. That interface is here. Oh, it's important also. This result shows us that this sample in this area is almost defect-free when you see the XY plane for our sample. And the Z, we don't know if it's defect-free, but the simulations give us that probably the thickness of this sample in this region is about 30 nanometers. Very good behavior for this 30 nanometers. Amplifying that region for the simulation, you see that this simulated image is matched completely with the structure. And here, the interface that is in this direction, 101 of the tetragonal unit cell. And these are the lattice parameters determined by the software for A and C lattice parameters in this sample. When you do this tetragonality factor, you see that it's about 12%. This is the same number that we have using using X-ray in the Newton diffraction in the Rietveld refinement. And they see that this is the zone axis is 100, and the polarization is in 001, because you have these atomic positions from our simulation. We have the atomic positions here. And it is we see here a very, very thin interface between separating two domains. Okay, how can we link these microscopic characteristics with some of the properties of the materials, with the properties linked with domain and domain wall? Here, once again, the simulation and this unit cell, pictorial unit cell, showing the direction of the polarization, and here the interface. This interface, when you see this interface, is an interface that you have a high concentration of atoms in comparison with the core of domain. And this first analysis using high-angle annular dark field detector that showed that there is a concentration, higher concentration of atoms in this interface. We can show here that this concentration is in fact high. This low magnification and the high resolution, they match very well the two analyses in two different equipments. And you see this interface, and you measure with the software 2.3 angstrom. And you can reconstruct this interface by using the information of our simulation, the simulated image, to reconstruct the domain wall or the interface in this case. And this interface, if you consider that this interface is, that the arrangement is good, is here, this interface has just this distance. It is your arrangement, atomic arrangement is regular until here. This interface has about 5 angstrom. If the second unit cell is also distorted for the very huge strain field in this region, your interface is still bigger, 9.6 angstrom, about 1 nanometer. And you see if this depends on the way that you prepare your sample. If you do quenching, if you put some strain, you can change this interface or the width of this interface, changing for example, if you have here a strain field in this region, or if you have here some electrostatic screening or where else, you can turn this width by changing your sample preparation conditions, or by, in this our case, by doping with lanthanum or controlling the concentration of lanthanum in our sample. You can change this. It's a flat interface that you can call now a domain wall that can be arranged. If you change the domain landscape, this can change as well. Here we see here the simulation, other region, the simulation, this interface. Here we reconstruct this interface. Reconstruct this interface for tetragonal phase. And here we see the angle, two theta angle. This is the angle between two different domains in this only geometric reconstruction of the domain wall. If you go 5 minutes, okay, thank you. If you see this image, if you can do simple calculations, you see that this tetragonality factor is related with the how these two octahedra of oxygen, they are pushed from one to other. If you change this angle, for our calculations by using X-ray diffraction and Newton diffraction, this angle is 83.15. And by using our high-resolution transmission electron microscopy, this number is very close to another. And you change the tetragonality factor, this interface can be stressed or not. What is the consequence? If you have a big or high tetragonality, your sample usually is brighter. Who process ceramics know that very tetragonal ceramics are usually brighter. If you change this lanthanum concentration, you tend to diminish this tetragonality factor, and the brightness is going down. The electrical conductivity can be changed here once you change the distance between oxygens and iron atoms in this region. Also the magnetic properties, because the super exchange is here in this region. If you change here this distance, you can affect this angle of the super exchange, and also the distance between the two oxygens or two iron atoms, in this case, that are doing the super exchange. If you have a proximity very low between these iron atoms, probably you can have also direct exchange between and have a ferromagnetic interface between the domains. Qualitatively, this can be used to explain some of these properties. And we have this landscape for domains and domains interface, and we did applied some electric fields, and you see that these domains they can be moved, and this hysteresis loop for this ceramic in a microscopic property that corroborates the microscopic view that we have here. If you change this domain landscape, probably you can change this. And that domain landscape can affect the overall ferroelectric and the magnetic properties. We did the same for rhombohedral, but and here in rhombohedral have a small tilt, only 3% between the two domains, but is okay, a very small tilt. This is the structure. The simulation for R3M, when you do the simulation for R3C is not good. The good agreement is for this space group. And we have these lattice parameters that are fit very well with X-ray and the Newton diffraction. And this is not tail to tail, but probably is head to tail arrangement of domains inside these materials. To finish my talk, I would like to answer some questions. The magnetic response can be turned by changing the structure into the magnetic backbone. The ferroelectric response by changing the domain landscape. And these materials can be applied in magnetoelectric device. And they also have how a site substitution works, change the structure and the domain landscape in these materials, and how to correlate size and scale effects. We not see one direct correlation, but our results indicate that our sample is very, very stable. The electrical potential is step at the domain node can be turned, probably, but our sample is thermodynamically stable. The electrical conductivity, probably, because it can enable stability of the domain walls. And for my acknowledgement for our agency funding in Brazil, this agency funding, our collaboration with Dr. Caixia in Helmut Zentrum Berlin, and the Dr. Eiras, and also André, that is here in this work. And I have a strong collaboration with the Dr. Eiras research group, and also with this institute in Germany. And thank you, everyone, for watching my presentation.
Thank you. Thank you.